Can we not walk into them? Okay.
Hi, screencast.
Why? Okay. Here we go. So we're gonna pick out the important parts. So, important parts. Here we go. We're gonna list out everything that we do know. Yeah, let's do that first. Let's draw a picture and figure out what the heck is going on. So it says a police cruiser is approaching a right-angled intersection from the north. So if we're approaching from the north, which direction are we going?
South.
Downward.
So north is like going up, right? But if we're approaching from the north, that means we're coming from up, going down. So this is where the police is. And we're going down, right? We're going down that direction. Okay, we're approaching a right-angled intersection. Okay, so that means 90 degree. And the car is going straight east. Okay, which way is east? If you think of a map of U.S., to the right. That's the way I remember it. I always look at the map of the U.S. So the car is going to the right. Here is where the car is. Do we have questions so far?
This is a police chase.
This is a police chase. We're trying to figure out how is the distance between them moving. But wait, distance between them doesn't mean, over and then across. We're meaning as a crow flies, as a bird flies. If you're a bird, you don't follow the streets. You just go straight where you're going. So I'm wanting to know how the distance between them is changing. So we got to actually label some things. So I'm going to call this Z, right? The distance between them, I want to call them Z. Yes, this is the hypotenuse because this is a 90-degree angle and a triangle. Just walk it over, okay? Walk it over. We're not going to be a sofa today. We're not lazy boys. Let's do this. It's a good one. Thank you. Okay.
I like that.
Trying to stop myself from being mad. Here we go.
So 0.6 squared plus 0.8 squared equals C squared.
Ah, yes. So, but first let's label our sides. I'm going to say the distance, right, this y distance is going to, the vertical distance I'm going to call y, that makes sense. Horizontal I'll call x, you can call it whatever you want, but it makes the most sense to call the vertical y and the horizontal x. Now, as he said, we can literally figure out what the distance is between these cars at this snapshot. So remember yesterday we talked about things moving, right? The police car is not going to stay 0.6 north. It's moving down. And the car is not going to stay 0.8 east. It's going, right? Just like the live speed chase I watched yesterday and almost missed the basketball game for. I was watching a live chase and they went right by my apartment. No, it doesn't stay stop. They almost lost the police and then they caught up to him. That's why I was late.
They got him?
Yeah, it was a woman. It was an old woman.
Oh, I love that.
She's going like 120 on the 118. Point is, the point is, these things are moving. They're not staying. This is a snapshot, right? It's like you take a picture, things stay moving. It's just at this one instant of time, this is the distances. So.
It's like, so it's like we've been doing. Oh my God, it all makes sense now.
What? Share it with us if you're going to be distracting.
You said you know.
They're just getting careless.
If I was too embarrassed to say what it is.
Guys, come on, show.
Are you kidding me? Okay. No, we're over it. We're going to move on. So. All right. So at this one instant, we can figure out the distance between the cop car and the car. So I know I'm going to have 0.6 miles is going to be y at my snapshot time. Now, y is going to be changing because the police car is moving, but at this single little picture, right? It's just a picture. If I take a whole video, things are moving, but just single picture. At this one instant, it is 0.6 miles above. And then at that one instant, the car is 0.8 miles from our origin, which is the corner. And so if we do Pythagorean theorem, square both sides, did we figure out what length it is?
Do we not take the derivative here? We do it later.
We're gonna use this equation, but later, right? Y squared plus x squared equals z squared. We're gonna do that after this. I want to figure out at that instant what is my actual z.
Oh, at the instant.
Yeah, at this instant, just at the instant that we took these measurements, what is the distance between our car? You shouldn't be talking. Okay.
1.
Yes. Exactly. Right? 0.8 squared is 0.64. 0.6 squared is 0.36. 0.64 plus 0.36 is 1. Square root of 1 is 1. So we see z is equal to 1. So awesome. Okay. So at that instant, they're exactly, yeah, it's a 3, 4, 5. Who would have thought I'd pick easy numbers for us? 3, 4, 5 triangle. I didn't pick the numbers, Miss Lincoln did. 3, 4, 5. We like picking easy numbers for this because we're trying to teach you the method. Okay. What else do we know? When, blah, blah, blah. Okay, so we already used this fact, right? How far it is. 0.6 miles north, 0.8 miles to east. Okay. We determined with radar the distance between them and the car is increasing at 20 miles an hour. Okay, so if we're increasing, wait, what's increasing? Which one? Which one's, which thing is increasing at 20 miles per hour?
Car.
The distance between the police car and the car. Z is changing at a rate of 20 miles per hour. So dz dt, the rate of change of my z, the rate of change of the distance between them is changing at 20 miles per hour. Because the distance between the police car and the car is the z. So that's changing at that instant, it's changing at 20 miles an hour. Okay. What else do we know? If the cruiser is moving at 60 miles an hour, okay, that sounds important, right? The cruiser, 60 miles an hour, which one is this?
That's Y.
Y, right? It's Y. And which way is it going? Up or down?
Down.
Down. So it's going to be negative, exactly. dy dt is going to be negative 60 miles per hour because we're going down. Now, the thing we're looking for, speed of the car. Speed of the car is which thing?
X.
dx dt. This is what we're looking for is dx dt. We don't know. I would like to know how fast is the car going. It was funny listening to the news people yesterday for that live chase because for points, for parts of it, this old woman was going like 30 miles an hour of traffic. Yep.
Wait, that's a movie.
How old is the woman?
Old. I had to stop and leave and go to the basketball game. Okay.
Yesterday?
Yeah. This is yeah, that's why I walked in with like 7 minutes to go instead of like 30. I was watching the speed chase. Steven actually found me and was like, "Are you coming?" "Yes, Steven." Okay. That was sad. All right. Yep. Okay, let's do this.
Us for one of our games.
I do.
Wait, I have a question. So Ryan,
I asked him if I could be assistant that day. He said no. Okay.
manager, he said no.
Okay, what's your question?
What if I answer?
No?
I
Don't do it.
understand that dy dt
dy dtk.
is decreasing by
Okay.
negative 60 miles per
Yep.
hour because he's going by 60 miles
Yep.
per hour. But are we not going to take into consideration the turn?
What about the turn?
Because the police car has to do a little.
Yeah, but none. All we're talking about is the rate of change at that moment that he is 0.6 miles above. How fast is he going? 60 miles an hour. So he's going 60 miles an hour down towards the corner.
I know what we're gonna do.
But I haven't, like, this is only at the instant, at the instant, he's that far away. That's how fast he's going. Clearly, he's going to have to, do his little Tokyo drift around the corner and try to catch the guy. But we're not there yet. We're not there yet, okay? We're only at the point where he's going just at that one point. It's kind of like we took a picture. Shh. It's kind of like we took a picture of him 0.6 miles away. And simultaneously, we can read his speedometer at that moment. So we know how far he is and how fast he is at that moment.
So this is what those little guns do?
Didn't I explain this yesterday? I explained this yesterday.
It was for
Yeah, okay.
distance. It was for
Not
distance.
speed. No, she explained speed and fast.
I did. I fully explained it yesterday.
Should we play the
It was a
Tokyo Drift
distance
theme
one.
Okay.
song?
No, I explained both. I explained both. Because if you can figure out the distance
Yeah.
and just do it over and over again through time, you can see how your distance is changing per time, aka its speed.
No, yeah, but then, so that's doing this little thing?
Sure. He just looked down at his speedometer and said, "Hey, I'm going 60." Then he held maybe it was the police air thing, I don't know, helicopter, and they're like, "Oh, we're over the police car, laser, how fast am I increasing this way?" I don't know, yeah, okay. Okay, here we go, here's our equation. We're trying to find dx dt. What's the next thing we're going to do? You have a question?
No.
No, you know what we're going to do?
Yeah, I think so.
What?
We're going to use the Pythagorean theorem again to find the derivative of x.
Yes, we're using Pythagorean theorem because that's relating things we know with the thing we don't know, right? We know at that moment x, y, and z, and we know how some of them are changing, but we can take the derivative with respect to time. So d dt of this whole thing. So this is going to be 2 times x times dx dt. Chain rule. derivative of y squared is 2y times the fact that y itself is a function of time.
Wait, what are we?
Wait, I'm a little lost.
We're taking the derivative with respect to time. X,
Why don't we know what?
because that relates x, y, and z. Because we have a triangle, it's a right triangle, and that's how we can relate
that's
them.
Our only equation. Okay.
Yes, that's the only thing we know for sure. So we know what x is, right? Because we know x at that moment is 0.8, and the speed it's going, oh, we don't know, but we have to solve for that. Plus 2 times y is 0.8 times the speed it's going, negative 60. Now I'm filling all of my stuff because I know what x, y, z, dz, dt, dy, dt. Did I mess up? Y, yeah, sorry, 0.6. Okay, equals 2 times z, which is 1, times 20. Perfect.
Oh, and we figured out what x is, so we can just plug it. Oh.
Yeah.
And then we also know that dx dt.
I just divide everything by 2 and it works.
Oh my gosh. Okay.
So, let's see. 20, let's see, 10 times 6 is 6. This is negative 36. Okay. 0.8 dx dt is equal to, well, hold on, minus 36 is equal to 20. Add on both sides. 56 times 5 over 4. Yeah. I'm not going to show, you guys can figure out the rest. You can do the algebra. So dx dt is equal to 70 miles an hour. Cool. That's how fast the car is going. Not exactly a high-speed chase unless you're driving by my apartment where the speed limit is 40.
Fast.
Yeah, it's not 120 like Grandma was doing yesterday, so.
Hey.
They like kept bringing that up. Just speeding down DeSoto, turns on she was old.
Like,
Oh, then that's
Like
the 120.
60-year-old or like?
Are we like?
I would say probably at least 60.
I feel like.
Okay, questions about this one? Guys, ready? We're gonna finish. We're not finished. Yeah? Questions?
Yeah,
Okay, let's keep going. Alright. No, it's okay. Read to yourself. So these last 2 questions have been stereotypical related rate problems, right? With a triangle. Oh, I forgot that I didn't.
Oh no.
Yeah, we already did this. So here's the other stereotypical one, giving you the different types of ways I can ask these questions.
Oh, this is a cylinder.
Yes, water runs into a conical, aka a cone, tank at the rate of 9 feet cubed per minute. The tank, in Nebraska, everywhere.
Cone.
Cone, because it's a funnel.
Okay, but then how does it like stay upright?
What?
what?
The water tank. No, it's.
There's literally poles that hold it.
Okay, what shape is a water tower? What shape is that?
Depends what water tower you're looking
And
at.
there's like the.
Yeah,
So, has many shapes. Okay, whatever. So, yes.
I'm sorry. For the test.
I'm about to draw it. About to draw this. Okay.
For the test, if we can do all of like these different types of equations, are we good?
Yeah, I mean, double check your practice test and you'll be fine. These in the practice test,
All
we should.
the equations.
No, I have faith in you remembering your previous math.
Oh, we have to know the cone formula.
Yeah.
I taught my whole.
Okay. This is. I wish I had good art skills. Okay.
That's a nice one.
That's a nice one. Okay.
Oh my god.
Here we go. So we have a conical tank, all right, literally a cone, and water's flowing into it. Okay, things we know. It has a height of 10 and a base radius of 5. Let me write those in. So right here, this height, right here, this height right here. This is 10 feet. 10, I want to make sure the screencast can see it. 10 feet. Wonderful. And it says a radius of 5. So ready, radius is from the middle to the outside. So this is going to be 5 feet. Wonderful. Are these going to be changing or are these constant?
Constant.
They're constant. It's metal. It's tin. You're not going to be changing the tin. No, we built the cone. That is constant, right? That size, done. We're done. It's built. The thing that's changing is water. Water's pouring in. Okay. So water, this is why I'm like, saying it, right? Maybe it's silly and you missed it right now, but hopefully you will not miss it on the test, okay? Or your homework, especially. Pay attention. Look for things that are changing and not changing, right? The material, the cone, not changing. Amount of water flowing in there, changing.
Oh.
Here's the water. Wonderful. Okay. Maybe I should have drawn like, no, this is fine. Okay, so the water is running into it at a rate of 9 feet cubed per minute. The tank's points down, has a height of 10 feet and a base radius of 5. How fast is the water level rising when the water is 6 feet deep? Okay, you know what that means? This length right here is 6 feet. I'm sorry, I didn't hear your snarky comment. What?
Nice.
Wouldn't it just be going in at the same rate? The rate wouldn't change?
Okay, so the amount of volume coming in, but the water level.
Oh, so
So if you think about it,
I thought I was saying what's the rate change?
I'm sorry, I thought it was a snarky comment. I apologize, and I stand corrected. I made a mistake.
Apologize to your snarky comments to him, but not me.
Yeah. Yes. False. Really? I let you borrow my calculator? Okay. Okay.
Really use your tongue.
Yes, it was good luck.
Okay, here we go. So things we know, right? Let's make it clear. Things we know. Water is flowing in at a rate of 9 feet cubed per second. So that's going to be dV dt, aka how is our volume changing per time? Literally 9 feet cubed per minute. 9 feet cubed per minute. Right? We're just pouring the same amount of water in per minute. But the thing is, right, we have a smaller volume at the bottom. So at first, the water's going to rise really fast. And then as we get more and more surface area, it's going to rise slower and slower because we have more like space to fill. Does that make sense? So at first, it's going to rise really rapidly and slow down, slow down, slow down.
Oh, because it's
Kind of like decay. The rate of change is going to be getting lower and lower. But you get it. Yeah, you see it. Okay. So what we're really trying to find is the change of height per time, right? We're trying to look for dH dt, right? So this is our height, right? And I'm just going to write it over here. Height is 6 feet. Makes it a little clearer. Because the water level is going to be changing. It's not just going to be 6 feet. At the moment we take a picture, 6 feet. But then as the water keeps pouring in, it gets higher and higher and higher. Okay, so do we know volume of, give you a hint. Cone-shaped pyramid things always have a third in front. So if it was a cylinder, you'd take base times height, right? Pi r squared times height, but it's a cone shape, so it's 1/3. 1/3 pi r squared times height. Okay. 1/3 pi r squared times height. This is the area of your base, which is a circle. This is your height. Anytime you have a cone pyramid, it's always 1/3 times it. Yeah, here you go, right? Pyramid. Ready? Any pyramid? Oh, base times 1/3 times height. There you go. So if you think about the similarities between all of these equations, there's not that many to remember.
Why 1/3?
That's just the way it works out. If you have a cylinder and a cone that are the same height and the same area of base, that's what it is. I'll just put it that way. Okay, so
Wait, that's wrong.
yes.
So we know h is 6 feet, but why do we not know dh over dt?
We don't know how the height is changing with respect to time. As we pour more and more water in, the height is going to be changing, but we don't know at what rate. So that's what we have to find. Okay, so interesting. We don't want to have two unknowns, right? Because as the water level rises, the radius is going to increase and the height is going to increase. Oh my gosh, this is a lot. We want everything in terms of one variable. So if there's some way to relate radius and height, that would be ideal. So we're going to throw it back to the old geometry. Yeah, geometry time. Okay.
I like geometry.
Yeah. Okay, geometry time. Here we go.
Yeah, we were playing.
So I'm going to cut out let me put this in different colors so you can see. I'm going to cut out roughly like this triangle shape. So, right, it's kind of like I take a slice. Yeah, I know, the water will fall out. Okay. So, it's a cone, and
I made 1, 2, 3, 4 people laugh, and I think that's good.
that is good. It's good to bring happiness in the world. I appreciate you. It's good. Okay, I cut out a triangle slice. So, I know the total height is going to be 10, and the radius is 5. So, at a certain time, right, I'll have a certain height and radius. I can use similar triangles.
No way.
to show the ratio
Really young.
and relate radius and height. So, if I say r over h, what is this equal to?
5/10.
Beautiful. And let's get r in terms of h. How do I get r equals something with h?
Multiply by h.
Multiply by h. R is literally 1/2 h, aka h over 2. There you go. Look at that. That's amazing. Yeah.
So now it's h over 2 squared.
So if I plug this in for our radiuses, let's see what the volume is. Volume is 1/3 pi h over 2 squared times h. So this is just going to be, let's see, 12 on bottom. So pi over 12 times h cubed. There, that's much better. That's so much better.
I have a cool question.
Because we know the relationship between radius and height. So now we have everything in terms of height. Yes, Maya?
Why can't you just plug in R and pi?
Well, we don't know what r is. Because here r is changing as the water. Well, as the water, no, because that's the radius for the top. No, it's not, because as the water level rises,
Oh, we're
The
calculating
water.
the radius of, oh.
because I want to know the volume is changing.
So do we ever have to find the volume of the whole thing? Like just the actual, no?
Nope.
So 10 feet for the like height of it is.
For the total height. Yep.
That's just.
But we're using the fact that we know the radius at the top is 5 and the total height is 10. So as I'm filling water at a certain time, right? At a certain time, I'm right here at a certain time. No, I need purple. At a certain time, go purple. At a certain time, I'll have a radius r and a height h. So I know I have similar triangles, so I can relate r and h. I'm literally talking to you, answering your question. Did you hear me? No.
Are you hearing me?
Yes, I was answering your question because you're.
I was the one talking.
Okay.
Sorry.
So, okay. Volume is pi over 12 times h cubed. Cool. Let's go ahead and let's see how is volume changing with respect to height, because that's what we're really trying to find. So let's take d dt of both sides. So dv dt, aka the rate of change, the rate at which our volume is changing, is going to be pi over 12 times 3h squared times dh dt, because chain rule. First, we take the derivative of h cubed. H cubed derivative is just 3h squared. And then we have to say, you know what, JK, that's not actually done, because secretly height depends on time. So there's an equation, right? There's a rate of change associated. So we have to use chain rule, because we're taking the derivative with respect to time, not height. So height is changing with respect to time, so we have to tack on that differential, that rate of change. Yeah? No? Maybe? Okay. Okay, so simplify this. So dv dt is equal to pi over 4 h squared times dh dt. All I did was take 3 and 12 and simplify. We know what most of these quantities are, right? dv dt we said was 9. Pi over 4. How much was our height? 6, exactly. It was literally given to us when the water was 6 high. Times dh dt. So we just have to get dh dt by itself. So 9 equals, let's see, 36 squares 36. 36 divided by 4. So this is just 9 pi times dh dt. So when I solve, divide both sides by 9 pi, I literally 1 over pi is the rate of change for my height. Divide by 9 pi on both sides, that's it. Okay, if you're wondering, this is approximately 0.318 feet per minute. So it's not changing like that much, about 4 inches in a minute. Okay, not too bad. But imagine if you're stuck in the cylinder because you're dumb and you decide to go swimming while your farmer dad is out there. Okay. Not to me, but not to me. It's just like people don't think about it. They jump in these irrigation canals or gravel pits. Gravel pits. Well, if you're stuck in there, and they're like giant tin walls. You literally have to tread water until someone gets you. Really? When this actually happened? No, there's people that die every year in the Midwest because the kids like go jump in the silo full of corn.
That sounds like so much fun. Are there corn silos where you're from?
Yes. And I'll never forget, when I was a kid, the big old silo in my town, like, fell.
What? That's so scary because I saw this thing of this guy in there and he had a harness.
Oh, yeah,
He's
yeah.
like, the harder he wants to stay up, the more he's.
Yeah, it's like a Newtonian fluid.
So weird is that?
So they should have like a door at the bottom, so when you sink to the bottom, you can open the door.
Well, corn goes out. All right. All right, let's keep going. Shh, let's keep going. All right, we have 2 more problems. Come on, ready and focus. 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 Come on. Just trying to give you a real life example where like things like this matter. Whatever, it doesn't matter for you. Okay. Example 7. Okay. I just have experiences other teachers don't. I'm pretty sure if you ask all the other teachers, I'm the only one who has ever raked hay or branded cattle or like anything country. So cool.
You bring
You like country music?
Yes. What? I grew up in Nebraska. Are you kidding? Yes. Okay.
Did that traumatize you?
4 out of 5 stations in Nebraska are country.
Did that traumatize you?
Okay. Let's go. Example 7.
No, did that traumatize you?
On the smell of branding is disgusting. All right. Example 7. Shh. Example 7. This gets harder. We're finishing this today. Let's go.
Oh, but the woman could be me. I'm 5.5 feet tall.
Cool. So, ready? Here we go. Hannah Fahuna is 5 foot 6 foot. 5 foot 6 inches. Hannah Fahuna walks at a rate of 6 feet per second towards a street light that is 22 feet above ground. At what rate is the length of her shadow changing when she was 15 feet from the base?
Wait, you changed it. Oh, never mind.
No, all I did was put your name in it.
Wait, Mr. Brian, can it be me? Because that's the closest I'm gonna get to 5'5".
Ariel
5'6", not 5'5".
is walking towards, okay.
5.5 feet, not 5.
Let's draw a picture. Guys, we got 2 whole problems to do. We gotta go. Okay, we're gonna draw a picture. Here is Hannah Fahuna. Okay. She's walking. This is the length of her shadow. That's an S. Shadow. That's the length of her shadow. Okay. We know that she's walking towards a street lamp. Okay. This is the street lamp. Kind of. There's the street lamp. There's a light on it. Okay. Street lamp. It is 22 feet above the ground. Now, the distance between Hannah and the street light, I'm going to call X because it's going to be changing, right? As she walks closer to the street lamp, the distance between her and the street lamp gets smaller.
And S change. Yes.
And S is going to change because the angle between, her and the light is going to be changing.
We find both.
No, what we're looking for is how is the length of her shadow changing?
Oh.
So drawing a picture kind of helps us. Now, things that we know. She is walking 6 feet per second. I don't know if I call it walk, trotting, right? She's trotting. It's kind of fast. It's 2 meters per second. 6 feet. Yeah, it's her taking out the short girl yesterday. Okay.
Oh my gosh, attacking her. Wow, you should have seen that from afar.
Okay, so
Her inertia was so
she is going, she's going towards the street lamp. Which thing is changing? She is going towards the street lamp. Which thing is changing? The X. Is it getting bigger or smaller? Smaller, because she's getting closer. So that's why dx dt is going to be negative 6 feet per second. Because she's getting closer and closer. X is getting smaller. X is getting smaller. The distance between Hannah and the street lamp getting smaller. By how much? 6 feet per second. Right? So we're decreasing X. That's why it's a negative, because she's closing the gap in between them. Yeah? Okay, cool. Make sure we understand this. Okay, what we're looking for is the rate of change of the shadow. How is the length of her shadow changing? So this is just going to be ds dt. How is the length of the shadow changing? Right? S is the length of the shadow. Okay, what was the key to solving the last problem? Give a hint. Geometry. What did we use to solve the last problem? What did we have to use?
Similar triangles.
Similar triangles. Do we have similar triangles here?
Yeah.
Yes, we do. We got this. Do we know? Okay, so I'm going to draw the 2 triangles right. Here's the small one, and then we have the big one. Okay. What is the length right here of the small triangle? S. What is the height of the small triangle?
I'd say 5.5.
5.5, exactly. It's her height. Bingo. Here we go. What is the length of the big triangle? Length of the big
S
triangle.
plus X.
S plus X. Okay, what is the height of the big triangle? 22. That's the height of street lamp. Okay, we have our two similar triangles. Now we have a ratio. We can okay. Yeah, maybe. Hopefully this is like walking you through, right? Draw a picture, see what you have, try to relate it to the picture. A lot of times you're going to be using geometry. Welcome. This is geometry part 2. Literally going to be using that the whole time. Okay, so I'm going to write a related rate. 5.5 over S is going to be 22 over S plus X.
Would be 4S. Right?
Cross multiply. Let's see. So I'm going to have 5.5 S plus 5.5 X is equal to 22S. And if I subtract the 5.5 on the other side, I have 5.5x is equal to, what'd you say, 16.5s? I'm sorry. My s's and 5s are kind of similar, so I'm trying to make it like curly-ish. Okay.
I like it.
So this is my relation between s and x. Because we know how x is changing, I want to know how s is changing. Hey, okay. Let me rewrite this thing that's really important.
To solve for x or s?
Well, what are we trying to solve for?
S. Because it says
This is my equation. This is my relation. Now, if I go through and take the derivative with respect to time of both sides, what I'll have is 5.5 times dx dt equals 16.5 times ds dt. We know what dx dt is. It's -6. Okay.
Wait, isn't the derivative of just like a random number that one? Oh.
But it's x. Derivative of
yeah,
x
yeah,
is
yeah.
1. But,
And that's-
then we got to tack on how is it changing with respect to t.
Okay.
So the thing we're trying to find is still over here. We see that ds dt, you can do the algebra. I believe in you. 5.5 times 6 is 33. Divided by 16.5 is going to be 2. -2. -2 feet per second. At that rate, that's how much your shadow is changing. It's getting smaller by 2 feet per second. Yeah. That's it for that problem. We got one more. Let's knock it out, right? Yeah. Let's knock it out. I'll give you a couple more seconds to write, marinate it in. The key to this, similar triangles, right? Geometry, literally. Think about the equations we've been using. Pythagorean theorem, volume of a cone, similar triangles, right? All the area of triangles, all this stuff. Your equation, most likely, you're going to be using a geometry equation or using geometry to create one with a relation. Okay, question? You have a question?
Never mind.
Okay. We ready to go on? Done writing? Okay, this last one. Hopefully it's starting to sink in how to do this. Water is being poured at a rate of 25 cubic centimeters per second into a cylindrical glass with base radius 20 and a height of 100. At what rate is the depth of the water, aka height, changing when the glass is half full? Okay, draw a picture. Here we go. So, I have a glass. This is roughly going to be like the glass I have at home, right? I have these nice little cups. When my sister got married, she gave me all her old cups. That was nice. Yep. And they're glass. I've only broken 3 of them. Yep. I should find. So there's I have a scar from one. Okay. Yeah.
So you can always remember.
It's so great. Yeah. Okay. Here's my cylinder. It's literally a glass. It's a glass. Oh my gosh. So, question, is my radius and height going to be changing? No, because sporadically it doesn't get bigger in your hand. No, that doesn't happen. Okay. Right, you know that. You guys know this, right? Just ready? Key to these problems is common sense. You got to be okay, what is changing? What's not? All right, you gotta use it. All right, so the radius of my glass is 20 centimeters. The height of my glass is 100 centimeters.
Is it 1/2 pi squared?
What?
Is it 1/2 pi r squared h?
Yeah. No, sorry, not 1/2.
I'm not at that.
It's not 1/2. It's just pi r squared h.
Oh, okay.
Sorry, I was not paying attention as I should. Okay. Other things we want to look for. Okay, let's make sure we have all of our like important things noted. Right, radius, good. Height, good. It's a cylinder, right? We know it's not going to be changing, right? That glass, it's constant, but the amount of water in there is changing. Okay, speaking of amount of water, our change is 25 cubic centimeters per second. So what quantity is that? Volume, right? The volume is changing. Cubic centimeters is volume. So dV dt is going to be 25 centimeters cubed per second. Are we increasing or decreasing?
Increasing.
Yeah, because we're pouring water into. It'd be different if we're pouring water out of. Hey, yeah? Gotta read the problem. Read the full problem. Okay, what else do we know? At what rate is the depth of water changing? So the depth is literally the height. So we're looking for dH dt. How is height changing as time changes? All right, and let's see. How is volume related to height?
Volume equals base times height.
Right, what's the area of my base? My base is a circle?
Pi r squared h.
Pi r squared times my height. Now, here's the question. Man, I have r and h, right? I have two variables that are changing, two things that are changing. Is my radius changing? No, it's constant. Literally, I'm pouring water in there. It's just going to be a circle the whole way up. My glass is not changing. It's not a cone. Constant radius. So that's helpful. If our radius is constant, I can actually make this into pi times 20 squared times h.
But you couldn't before because there was already water.
Because the cone had a changing radius. As water was being poured in, the radius of the...
It was,
Mhm.
I see.
For here, when I'm pouring water in, it's just a constant radius. Okay, so my volume is going to be 400 pi times h, because 20 times 20 is 400.
Bless you.
Okay.
Take ddt.
Exactly, ddt of all. So, dv, the amount of volume is changing per time. My rate of change of volume is equal to 400 pi times dH dt.
Wait, wouldn't, never mind.
So 400, let's see, 25 over 400 pi.
1/16.
400 pi. Hopefully that is right. Yeah, it's 1 over 16 pi. Or no, sorry, 1 over, yeah, 16.
Wouldn't it be 400 pi times h times dH dt?
No. Because, okay, ready? If I was taking a normal derivative, right, d dx of like 2x, what's the derivative?
2.
2 times that, right? The x goes away. So the derivative of 400 pi h is 400 pi, and then I have to multiply by the fact that h is changing with respect to time.
Okay.
Yeah. Okay, divide, so 1 over 16 pi is dH dt.
Aren't those supposed to be?
Yeah, they are. Is that your pad? Yeah, okay, your iPad? Okay.
I didn't want to pull my calculator. Sorry, I'm sorry.
What did you get when you did this?
It didn't register the pi. It just said 25 divided by 400. Do you want me to ask again?
Go for it.
That's
What's 25 divided by 400 pi?
0.0199 centimeters.
Wow, technology is just like crazy.
So I think you divided by 400 then multiplied by pi, or what'd you say?
I said what's 25 divided by 400 pi?
Oh. It's all right. 16 pi, that's about 48, so that sounds right.
Oh.
1 over 48. 16 times 3 is about 48. Okay, yeah. So that sounds about right. This is the answer I came up with when I put it in. Okay, this is dH dt. That's how the depth is changing. It's literally 2 centimeters per second. So remember the other one? We said at that moment it was changing 4 inches per minute. That's slower. This is way faster. Because this is way smaller of a volume versus that cone was really, really big. Okay, so that's it. We do have 10 minutes left, so I'll give you the choice. Do you want to, or do you have the capacity to be able to work on problems for 10 minutes, or do you want to start the practice
Can we
test?
start the practice test? Is that pop wrong?
It is 3:10. Oh, we only have 5 minutes. You're right, I forgot. I can't let you out early. Okay, we'll do the practice test tomorrow.